howdy all. Cheers for making it to the end. I know the bar's open, but cheers. So this is Introduction to Adversarial Machine Learning and Other AI Attacks. So a little bit about me. That's my GitHub where all my stuff is. So started in robotics, moved into AI, ended up in pen testing. It's been a journey. So I did my honors in multimodal neural networks for classifying fabric waste for textile recycling. It's a super awesome cause. If anyone is interested, let me know and I can put you in touch with some awesome people. That's really how I got started in AI. Otherwise, there's just some other generic stuff there. I'm a pen tester for TML. Shout out to them, they're tremendous. So the goals for today, so just go over adversarial machine learning and the risks posed by it. Then going to go over the MITRE adversarial machine learning threat matrix. Then cover the basics of Gans and risks that synthetic media currently poses. And then a couple different defenses. So artificial intelligence, really it's just something that seems smart. It could be decision trees, it could be machine learning. It can even be if statements. So really it doesn't matter what's going on in the back end, it's just trying to act intelligent, really. So machine learning on the other side is something that learns. So it's usually split up into supervised and unsupervised learning. Most of the AI you see in the news these days is machine learning based. And it's used in security for things like antivirus. So why threat model AI attacks? So self-driving cars, I think, is a great example of why AI is becoming a bigger and bigger issue, and you don't want a self-driving car falling for pretty much the oldest trick in the book. So this one didn't actually happen, I feel obligated to say. This was a fake news, but it's a genuine concern. Like, at what point do you declare something a tunnel? Because you don't want your car driving into it. So real-world AI problems. So this is a bit of an old one now, but I think it's still the best example to go to. So Tweets was a project back in 2016 where you could tweet at a Twitter bot and it would learn from what was tweeted to it. And it started off pretty nice. So this was, I believe, day one. And then by the next morning, it got a little weird. And then a little later, it got a little less nice. And then by the end, it was, the entire project had to be scrapped in less than a day. It was an absolute mess. And it just goes to show that if you're not thinking about these kinds of issues, problems will occur the same way they do with every other piece of software. So we're going to talk about two-dimensional data just because it's nice and you can see it and it's nice and pretty, but this can go out to the nth dimension, so these could be images. So this is my favorite example, and essentially this is just a 100 kilometer by 100 kilometer map where a kangaroo, crocodile, and koala has all been found. I don't know how well you can see it, but it'll get easier in a second. The question is, based on where these three were found, where would you expect to find more kangaroos, crocodiles, and koalas? So the way we do this is by essentially building these nice boundaries. So what we've done now is essentially what's called a model. We've just drawn some lines, and we've said anything on the left is going to be a kangaroo, anything on the right is a koala, anything down is a crocodile. Easy enough, but is this a good model? Who knows? So here's 4 different examples of equally valid models. And I've just drawn random stuff. They all have 100% accuracy. Which is the best? How do we find out? We just add more data. So once you add more data, you can then go back to your models and see how accurate is it now. And essentially, as you can see, none of these are particularly accurate. Top left gets pretty good, but it's still not great. So then what we do is we draw some better lines. And then now that we've got this, we can add more data, and then we can just keep working and working and essentially get the best boundaries we can. So yeah, the big takeaway here, more data, better models. The issue is what happens when you have lots and lots of data and it's a little messy. So with something like this where the data's kind of all over the place, you have 2 big options. You can either just draw some kind of rough lines and get reasonable accuracy. So I think this gets around 80% accuracy. Or on the right, you can see this one gets perfect accuracy. But it's very zigzaggy, it's very wonky. So question for the audience, which of these models is better? The left. Exactamundo. Yeah, so the 80% is actually better because you're not relying so much on individual data points that you're working with. It's a little overlappy. But yeah, so this model on the right is what we'd call overtrained, which essentially says you're just paying too much attention to your actual data points that you're working with for training, and you're going to end up with having all these little errors. But this kind of takes us to the big problem, which is when you're modeling for generalization, which is not the data you have, but the data you don't have, you're going to end up with some inaccuracies, because 100% isn't necessarily the goal. So misclassifications happen when stuff like this occur, so especially in overtrained networks, but even in regular networks. So I've just zoomed in on pretty much the hotspot where you can see that one orange data point. Sorry for anyone who's colorblind, this square. Actually, I think it should be all good. Because of where that square is, it's taken a whole bunch of data, which should probably be a different one, and just a few different changes to the x and y coordinates gives you an entirely different class. So trying to find where these little weird spots are essentially what you're trying to find where misclassifications are. So neural networks are really just a fancier version of this. So you don't really need to understand exactly what's going on here if this is a kind of new diagram to you, but essentially the model is the background and the dots are the data points. And that thing on the right, essentially what we're doing is we're just slightly changing this model, and then if it's more accurate, we keep the changes, and if it's less accurate, we throw it away. And then you can see it eventually shifts and gets all the blue in the center, and then the orange goes on the outside. And you can get these even more and more fancy by just expanding how many nodes they have in them. So this is a far more complex model, and it's a little hard to see, but essentially it's just two spirals. And something like this, it has a lot of difficulty trying to classify. You can see even where it kind of caps out in accuracy, it's still weird and wonky, and it's an absolute mess. So this takes us to the big issue with machine learning. So the fundamental weakness in machine learning comes from the fact that we don't want things to be 100% accurate, so some things are going to be misclassified. So as attackers, we just want to find the things that are misclassified, or in some cases, we can make things misclassified. And this could be to bypass a safety feature, to avoid antivirus, or just to cause general havoc, like in the Tabot case. So the threat model that we're really working with is all of the different moving components. So you can see them all there, and it's split up into two sections. You've got training and inference. So training is anything while the model is learning, and then inference is once it's learned and you're trying to ask it things, so trying to figure out what classification something should be. Yes, the important point there being. So whichever parts of this that your users can touch are the parts that are going to be at risk. So for Tabot, it was the training data. So there's just a few other key things to kind of cross off before we can get into the meat and potatoes of this. So unsupervised learning is the alternative. So everything we've looked at so far uses labeled data. So you have your data points, and you know that it's a kangaroo or a crocodile or a koala. So unsupervised learning works off unlabeled data. So it's way cheaper because you don't have to have someone going through every single data point figuring out what is this. So essentially you just throw all the data at an algorithm and let it try to figure it out. So it's a great way to verify your data set because it's very quick, and then you can move it on to supervised learning. And the best example of this is k-means clustering, which essentially, for each number of classes you have, so in this case we have 3, you just take a node, which is your classification node, and whichever data point it's closest to is the class it'll be. And then you move each of those nodes to the center of their cluster, and then just rinse and repeat those 2 steps. And eventually they'll all tend to shift towards these big clusters of data, as you can see there. And I'll let it play out for a little, I'll let a full set play out so you can see it in real time. So it starts off with everything being blue, and then blue shifts up and to the right, which makes red go up, which makes green go right. And then they all end up reasonably accurate. So the question is, really, so data sets can come in all shapes and sizes. So here's 6 random data sets. And the question again for the audience is, how do you cluster these different data sets? And there's no right or wrong answer here, but it really comes down to what the data actually has. So for example, when I see the 2 ring data sets, I expect that the center ring will be one class and the outside ring will be a separate class. But that might not necessarily be correct. It could be a left-right split. So when we look at k-means with this is how it gets them. So I would say for the 2 circle data sets, this is incorrect. Same with the upside down U and the right side up U, and then the stretched clusters as well. But it really comes down to what is correct. So you don't have to look at everything on this slide, but essentially I've just taken a bunch of different algorithms so you can see they all work differently, which is a problem if you're using this for a problem because you're going to get different results. So they definitely have a great use, but they have a lot of problems. And then there's just a few little interesting ones I've kind of picked out to kind of show off the different ways that things can get clustered. Yeah, so the issues with supervised learning and the reason why it's not used for everything is all data is equally valued. If you can control the inputs, you can control the results. It's vulnerable to supply chain attacks. If no one's labeling your data, how do you know it's labeled correctly? Or how do you know that it's the data that you're expecting, for example? Each algorithm has its unique quirks, so if you know what algorithm they're using, you can cater your attacks based on the biases that that specific algorithm has. And of course, because if you know the data set and the algorithm used, you can just replicate the model yourself. And if you have a model, then in general, you've pretty much won in this kind of space. And because it's less accurate, it's also just more vulnerable to brute force attacks. Transfer learning is one other quick thing to cover off. So essentially, training neural networks, it takes a lot of time, it takes a lot of work, it's expensive. So it can generally be helpful to start with a model for a similar problem and then just work it into your problem. So there's far more dog classifiers than there are koala classifiers. So you can start with a classifier for a dog, get some photos of koalas, and then train it on the photos of koalas, and take what it knows about classifying dogs, save you a whole bunch of time. So images. So why are images hard? So this is another fun rhetorical question. Which of these are stop signs? And more importantly, if you were programming a self-driving car, which of these would you want a self-driving car to stop at? Let you all ponder it for a bit. Yeah, this is it. Lots of, I guess, like questions to keep you thinking. So, personally, I would want it to stop at pretty much all of these except for the bottom 3 and the lollipop. But again, the real issue is that even the classifications of images is a very tricky. Even the classifications is a really tricky thing to kind of get right. Oh, sorry. Easy. Hello. Excellent. Images are super difficult. Should you trust a backwards image, a color inverted image? It's really up to you. And then those bottom 3 are just a little Easter egg for later. But if you thought any of those were a stop sign, you might be a robot.
Well, shit.
Found him. So this is just an awesome quote I found. So images are to machine learning what JavaScript alert is to XSS. So images, super complex data, and the classifications are all real messy at the best of times. So these are the best thing for looking at to kind of expose these problems where they lie. So MITRE, Microsoft, and a bunch of other companies got together in 2019 to try to classify all these different vulnerabilities and risks. So if anyone who knows the MITRE attack framework, it's very similar to that. And essentially, we're going to go through all the pieces in orange, which are just all of the attacks that are unique to machine learning. Essentially, they just found, I think there was about 19 case studies of real-world attacks, including Tabot, where AI caused a bunch of issues, and used that to kind of quantify where these attacks come from. So it's not all-encompassing because it's only talked about attacks that are real as opposed to the theoretical ones. But it's an awesome starting point. And again, if you're talking to business people or C-levels, they love these kinds of diagrams. So starting with Recon. So everything in Recon is going to be about trying to figure out what the machine learning models are doing, trying to get your own copies of them where possible, because as previously said, if you can get your own copy of the model, then you're in for a really good time trying to attack these things. So it's kind of split up into 2 things, family and ontology. Ontology are all the really specific things, so can you figure out what data set it's using, can you figure out the exact structure of the model. And then family's a bit more vague, so if you can't figure that out, do you know if it's working off just images, is it working off images and audio? Do you know if it's a deep neural network versus, say, a convolutional neural network? And then what kind of output is it giving you? Is it saying this is a stop sign or is this not a stop sign? Or is it trying to recognize one of 1,000 objects? Gathering data sets, if you are trying to attack a koala detection machine learning algorithm, then you need to get yourself a data set of koalas that you can work with, because otherwise you're going to have a very bad time. Where possible, you want to replicate the model. If you can interact with the model that you're trying to test, then you can just ask it to classify things for you, and you can get a far better idea of what it's actually doing, rather than trying to just copy it off data you find online. And same with going back to transfer learning. So if you know that it's a transfer learn model, then grab a copy of that model that it started with. And again, it'll have a lot of pre-built biases that you can keep an eye on when you're attacking yourself. And then model stealing. So anything that's client-side, for example, or so for example, any kind of offline antivirus, that model needs to be somewhere that you can access it. So if you can just get a copy of the model yourself, it will be very handy. So exploit physical environment is also under Recon. I'm not too sure why. I'm yet to figure that one out. So the big thing there is apricots, which are the same thing from that stop sign slide. So essentially, neural networks are trying to figure out what these different objects are, but they're really only trained on photos, which is what you'd expect. But it causes this issue where when you throw out a bunch of random nonsense, like in the top right there, in this case, this object recognition AI just sees it as a suitcase or a handbag. So just by throwing enough randomness, you can just physically print out these random images and just like give it a spin or just like wait for it to kind of click as something it shouldn't, and you can cause all kinds of issues. And then physical obstructions, the amount of facial recognition AI that doesn't work when people have masks is crazy, especially in COVID times when everyone's got masks on. If this isn't a risk you're prepared for, physical obstructions are a pretty significant thing to be concerned about. And then just OSINT. So how do you get all this stuff? Open source intelligence, you can go through all these yourself. I've just got a little case study here. So Luxury was a company that did a Kickstarter back in 2014 it was essentially an app which would take a photo of your face, and using AI, it would do custom filtering. So it could say things like remove blemishes, or it could do all kinds of weird things like give you like the face of a dog. So they just put up their Kickstarter, as everyone does, and there's a panning shot where essentially the engineers are sitting at their whiteboard and they see this face. And whether or not they're still using this, we can't really tell. But what they might not have realized they've done is they've shown you what anchor points they were using for facial recognition, which is very, very helpful if you're trying to attack this algorithm. Following up on the Luxury story, so in 2015 or 2016, I think the patent was filed in 2015, Luxury was purchased by Snapchat. And then directly afterwards, Snapchat, I'm going to have to slide to this slide because I can't read that one from here. But so when Luxury was purchased by Snapchat, they immediately filed a patent for very suspiciously similar technology. And patents being open, being publicly readable, you can then look through and try to figure out what kind of technologies it's using. Which again, there's a lot more information out there than people realize. It's far too small. Yeah, object recognition-based photo filters. So if you are trying to, and this is the current Snapchat app that everyone's probably or probably not people in this room, but the public is more often using to do all those strange filters that make you swap genders and look like a dog and all that stuff. So moving on to initial access. So the big thing here is backdoored, in this case backdoored models. So transfer learning, if you're taking someone else's model and you don't know what data it was trained on, you're opening yourself up to backdoor attacks. Same with if you're purchasing a model. Really anything you haven't trained, it's a common pretty big issue in machine learning that it's very difficult to figure out if a model has been backdoored until you have backdoored data that it's working incorrectly against, which is a really big issue, as we'll come to see. So then onto execution and persistence. They are two separate columns, but they have the same risk, so I've just put them together. So in this case, unsafe machine learning models. So for example, Python pickles or serialization is the most common way I've seen to store machine learning models. If you unpickle something untrusted, you can very easily get code execution. And then the bottom right there is just a little example of just how trivial it is to put code execution in a pickle. And then also backdoored sample code is another thing. It's the same in every industry, but especially, so the top right there is just an example I grabbed online, which essentially just downloads an image and then opens it to look at the data set before you do machine learning. But it's very similar functionality to what you might see in some kind of malware dropper. Always pay attention to what code you're running to test things. So model evasion is the real kind of interesting part here for me, which is essentially how can we misclassify data and what kind of problems can we cause from misclassifying data. So in the Taybot example, this was a data poisoning attack, where essentially untrusted data was going into the system and causing all kinds of problems. So we'll go through each of these more specifically. So my favorite evasion attack is adversarial noise, where essentially you just start with an image that's correctly classified, and then you just slightly change the image, and then ask the model. So the preconditions for this are you need to have a copy of the model that you can essentially ask, hey, what classification does this have? And your goal here is to try to misclassify something. So essentially, you can just start with an image that is correctly classified, slightly change it, and then ask the model, hey, is this more, does this look more like an owl than it did a second ago? And if it says yes, and you're trying to turn a turtle into an owl, then you just accept that change. And very similar to how we were training models earlier, you just do a couple changes here and there, and eventually you end up with a nice little graph like the one there, where in the top left, you've got my turtle that I see as a turtle, and the model sees as a turtle. And then in the top right, to me, it still looks like a turtle, but there's a couple weird pixels, and that's enough to throw off the model and makes it think that it's an owl. And then the same in reverse, too, for my owl turtle. Absolutely adore that graph. It's just the best. Oh. For a fancier example, Adversarial JS is the best thing I've seen recently for this, which essentially it'll take a bunch of different models and a bunch of different data sets, and in a few seconds, it can misclassify anything into anything. So in this case, it's just a handwritten data set. So it's at the start, it's a 0, and then by the end, it's an 8. Definitely have a look at this site later. It does far more fancy things than this, but I think it really gets the point across. So online versus offline evasion, it's pretty similar to passwords. Offline attacks are just way quicker because you can interact with it yourself. Online attacks still work, but entirely depends. So how much feedback is it giving you? If I upload a photo of an owl, is it going to tell me the confidence of a turtle, or is it just going to tell me what it thinks the most likely thing is? And even then, will it tell me the confidence level, or just, nope, this looks like a turtle to me? The other thing being, of course, if there is an online model, can you just build yourself an offline model and then run the exact same attack? So data poisoning, so again, from the Taybot example, but I think it is nice to see it in 2 dimensions. So essentially, if you can add data to the data set, which will then get classified, if you put enough of it in, eventually the classification lines will have to change to accept your poisoned data as part of the section. And the big concern here is not only is there now incorrect data in there, which might invalidate the whole data set, but when you classify off this, not only will it classify those wrong, but it'll also take a lot of other sections which should be correctly classified with it. So as you can see where those blue ones are, it's taking a whole pile of what should be the orange space with it. So for another case study, so I'm sure you've all suffered through enough captures in your time to be familiar with this. But yes, so currently Google's reCAPTCHA program is trying to classify footage from cars to try to, I presume, bolster their self-driving car capability. From this and the fact that they're trying to get people to label their data for them, you can kind of presume that they're trying to use supervised learning for something. So they need people to classify, to label their massive data set. So they've decided to crowdsource the process by getting other people to do it as part of a verifying you're a human process. So by definition, this is going to open Google up to a data poisoning attack. But how have they managed this risk? I think it's always good to look at the risk profile of the attacker. What are they getting out of this? So in this case, the attacker's just trying to harm Google. So they want to poison the data set by, in this case, labeling non-fire hydrants as fire hydrants. But really, it could be anything. So can the attacker affect the data set in any negative way? Could the entire data set get invalidated by this attack? Or even worse, could this lead to this data set being used in production and accidentally killing someone? So is Google defending against this? I don't know. Google's pretty tight-lipped about this kind of stuff. But I know that if I was given this problem, the important thing for me that I would absolutely drill into anyone touching the project is that you cannot mark data as trusted until it's been consistently marked a single result, which from what I gather is the same thing that Google's been using, where essentially they will throw the image to 100 different people and then figure out what they're all classifying it as, and then just trusting that enough of them are marking it the correct one. But then, who really knows? So model poisoning works the exact same way as data poisoning, but rather than poisoning the data, you're just having poisoned data and then training a model on it, and then giving that model out to the world. So on the left there, you've got 4 cars, then 4 dogs, then 4 boats, but each of them has got a nice little border. So if you build a model, if you build a model with a data set based purely off this, it will still classify dogs, boats, cars reasonably well if they don't have any border. But if they do have one of these borders, it will pay no attention to whatever is inside it, and it will just classify based off the red, green, the blue. So if you were given a model for, say, transfer learning, and you didn't realize that this had happened to it, you're probably just going to throw it a photo of a dog, and you'd be like, yep, said it's a dog, thumbs up, put it in production. But it is very, so it's very, very difficult to try to figure out when models have been backdoored like this. And then I've just put another example there of a cat and dog project where they put a little PyTorch logo. So exfiltration. So membership inference attacks are essentially when you're using data for these kinds of things, are you using sensitive data, and is there any way to extract that sensitive data? So if, say, for example, there was a facial recognition database and that data is supposed to be sensitive, is there any way that you can kind of extract it by sending it malicious samples? It's a little fancier than that, but the basic gist is you need to be being very cautious about what kind of information you're giving back in case there's any way people can kind of infer what data is coming back. And the same with model inversion. Essentially, you're just trying to reconstruct private data by asking the model whatever kind of questions. So this is a purely theoretical example, but I think really brings this point home. So NSA's next-gen firewall is a great product that probably does not exist, I hope, for this exact purpose. So back before Eternal Blue was known to the world, and NSA was using it for whatever they were doing, I could picture the scenario where a C-level executive was like, hey, this is a vulnerability that we haven't told Microsoft about, so we are currently vulnerable to it. How do we defend against this? And then someone could say, oh, you know, if we put it in like a firewall rules, someone might be able to figure out what's going on. So like, we'll use like a next-gen AI for it, you know? To essentially just train it on a bunch of different Eternal Blue exploits, and then, to train it on a bunch of different Eternal Blue exploits, such that it can then just drop any malicious requests and be like, nope, that's Eternal Blue. But then when you look at a model, it's not particularly useful to try to figure out what it's doing in general, so it's generally safer. So if this was up on a production system and you sent it a request and say you were just sending it a bunch of A's, for example, and something gets blocked, you could eventually start just changing your data ever so slightly and figure out what it is that it's blocking. And the question here is, could you, from something like this, given enough time, be able to reverse engineer an Eternal Blue vulnerability back when it was not known to anyone? So there's lots of interesting edge cases to consider when you're implementing this kind of technology. And then, of course, going back to model stealing, so if you can either steal an exact copy or even if you can just replicate it, for a lot of these AI companies, the model is the intellectual property that they're trying to defend. So if you can get a copy, that's super important, and they will absolutely love to hear about it. And then impact, of course, always got to be there to scare off the C-levels. So all kinds of things, defacement, DOS. 3 that I've added that I think are important enough that they should get their own kind of points. Reputation damage, as with everything, even the Taybot, it was, whenever these kinds of catastrophes happen, I think it's always good to drill home that point that reputation damage matters so much. Bypassing defenses for things like silence or virus total, anything that's using AI. Bypassing defenses, if that's their business, is to block you and you find a way around it. Again, that's going to cause all kinds of problems for them. And then crypto mining. So especially in the training side as opposed to the inference side, a lot of the software, a lot of the hardware that is training these models is super GPU intensive. So they usually have these massive rigs. So I'm yet to see one, but I would be very surprised if we don't in the future see crypto mining vulnerabilities going around or just exploits to try to take advantage of these ludicrous GPU setups. So defenses are still a work in progress. No one's really sure what is going to be the best way. So some of these are my ideas, some of these are other people's I found online. So for model protection, so for offline evasion, you just need to protect your models as much as you can. So encrypting models on disk is a little thing, but again, goes a long, long way in case any one of a whole number of different web vulnerabilities exist, for example. Don't use client-side models when you can avoid it, and where you can't, definitely find whatever kind of protections you can. Canary models, similar thing. As with anything sensitive, if you can put canaries in and figure out if someone's accessed it, at the very least you know, and then you can do damage control based off that. And then paper towns is an idea of mine based off, so when people used to make maps back in the day, they would put a fake town on them, such that if someone else copied their map, they'd be able to realize that they had evidence that the map had been stolen. Similar thing here, again, I'm not too sure if it's going to work out, but it's something I've been exploring, is can you put a similar thing, can you put a paper town into your model such that if someone does steal it, you can prove that it was stolen? And then offline evasion, online evasion, sorry, just don't return confidence levels, tell the user as little as they need to know. And then rate limiting requests also does a lot, especially for if someone's trying to copy your model and just throwing data at it. That makes all the difference. So for the evasion attacks, the big three here, data modification, admission control, and multiple assessment functions. I'll go through each of them more specifically because they're a bit busier. So if you can modify data before it gets classified, so doing a similar thing to how you would salt passwords, yeah, so if you can modify data before it gets classified in such a way that even if someone steals your model or has replicated your model, they don't have whatever this new secret is, essentially you're pushing the onus off the model, which is at least inferable to some degree, and putting it onto a new secret that is more protected. And then just a couple other points I put there. So if you derive the salt for each image based off the image, then you still get consistent results all the time, whereas if there's some kind of randomness between two different models, then you're going to have issues. You can also modify it in some other way. So what happens when you flip it, change the colors, sharpen it, smoothen it, classify different portions of the image separately. The concern with all of these is that if you're modifying the image, then you're not classifying the image that was given to you, and that has a whole bunch of risks to consider. So for admission control, so going back to our noise example, whilst to us you can see there's something a little wrong with the image, you might not realize what's wrong with it, but it's enough that to the human eye you can say, nope, this is something weird, and if it's not mission critical and you can just drop the image, then dropping the image is a totally fine way to go about it. So yeah, just block images that are too noisy. You can also try denoising images, but you have the same issues where you're modifying the initial thing. You can do things like measuring the gradients between the pixels, which is a thing that's done to identify photoshopped images. Same thing, and that'll kind of help you figure out if images have been tampered with before they got sent to you. If attackers just use noisy images, like blocking noisy images seems like a great solution. Is there any reason we can't deal with that? And again, it's super contextual. So ultrasound information is very, very noisy, and every problem has a different data set, and they each have their own unique quirks. So there's all kinds of different data sets where blocking noisy images just isn't practical. So multiple assessment functions comes in three different kind of ways. So this one here is multi-classification. So in this case, it has three different models that you're checking each data point against, and up to your own risk tolerance, you could say, only accept an image if all three models get it correct, or you could say only if 2 of 3 models get it correct, and the goal here is just to avoid those little bits of variance you get from a single model. Multimodal is the one that I recommend where possible, which is rather than classifying just based off of the single image, you classify based off 2 separate data streams. So if you have video data, if you classify on audio and image separately, then it becomes far, far harder to do these evasion attacks because you have to work off 2 different functionally dimensions of data. And then multi-scan is another option for something like a self-driving car. If it's not, if a self-driving car isn't sure whether something's a fire hydrant, maybe it's 80% confident where it's usually 90 because someone's tampered with it in some way. You have real-time data to work with, so you can take another 10, 20, 30 photos and then classify each of them, and ideally you can kind of reduce this risk. Further research into this stuff that I'd recommend, read the case studies on the MITRE Adversarial Machine Learning GitHub page. They're all there, and they're definitely the best way to kind of see the real-world impacts of these kinds of things. Build some machine learning models. It's the best way to kind of get a deep dive. If you want to help develop some new defenses or hit me up with ideas or reasons why my ideas will fail, I'd absolutely love to hear about it. And then help with the project. It's still super new, and they're all super interested in things kind of picking up. I'm just going to briefly touch on Gans because they really deserve their own talk, and maybe I'll do a follow-up on at some point. But essentially, so Gans are the most terrifying thing in the world, in my humble opinion. So the way they work is that rather than having a model to classify data, they work off generating data based off whatever you kind of ask for it. So in this, if you were to ask it, hey, where would I find a kangaroo based off this model, it'll just point somewhere in that section and be like, here. So if you wanted something more specific, you could say, hey, where do I find a kangaroo, a crocodile, and a koala along that, that black line there, along the 40 kilometers on the y-axis? And then it'll just pick a random spot on each. So the risk here is that once you build a GAN, or once an attacker builds a GAN, they can create a nearly infinite amount of valid data points against the rival model that they're trying to beat. So real-world examples of this, synthetic media is the real big concern. So things like deepfake, and I've just put resemble AI here. So anywhere where you can essentially simulate biometric data is a really big concern. So resemble AI is a project where they insist that the lowest I think they've got is 50 words, that if they have 50 words of voice data, they can replicate like 99% of the English language. And then they have a couple examples there. So for example, if you wanted Homer to insist on a nuclear launch strike, something you could do. All kinds of concerns there, which I think is going to just get bigger and bigger for vishing. The amount of executives or political figures who have enough voice biometric out there that this can be exploited is a really big concern. And then there's things like two-factor auth that can help with this, but again, no one's really sure what the best thing is, and the laws to defend against this kind of stuff are falling far, far, far behind. Yeah, so defensive GANs. So the good news, no GAN is perfect yet. So if you can identify the issues with a GAN, then you can catch it using the same techniques as the defense for evasion. And then most of these projects, including the one I just mentioned, all have a rival project to try to identify malicious use cases. But it is very much on a case-by-case basis. If you can't figure out how it's being generated, you're going to have a worse time trying to defend against it. And thanks for listening. Slides will be up on my GitHub with potentially some exercises if I get around to making them if you want to try to hack some of these models. Hope you all learned something or gained some new perspective. Otherwise, cheers.
Round of applause. I know it's the end of the day, but has anyone got any questions for Edward?
Hi, so I have two questions. The first was when you talked about the defenses to sort of some of these attacks, a lot of the defenses you presented, such as altering your data before your model classifies it, rely on essentially introducing systematic error into the model. What are your thoughts on really giving systematic error can be, essentially modeled by an adversary and plotted afterwards, you can sort of correct for it. What are your thoughts on the sustainability of that sort of approach on mitigating attacks? And then my second question was, when you look at academia, there's sort of this very rigorous understanding of the need to sort of, choose proper sampling methods, ensure that your data is really appropriate before sort of trying to create statistical models for it. This is really rigorous approach. So, when you look at medical studies, there's, you see things like double-blind studies, those sorts of things. But then in IT, where it's sort of like this very applied discipline, there's not as much of a rigor in that. Do you think that, how relevant do you see sort of that sort of academic approach to data to AI? Thanks.
Excellent. Yeah, so as far as modifying data before you classify it, it's definitely a concern is that it just becomes a cat and mouse game and everyone defaults to changing something a specific way and then people adapt to that. Essentially, yeah, if you can figure out what the change that they're doing is, then you can do these exact same attacks, especially offline. It becomes trivial to try to work around. So, yeah, no one's really found a great solution yet, which is part of why I find it such a fun field. So it's definitely still super new, and I'm not too sure how people are going to crack it in the end. But it's definitely a way that I think has some merit, especially things like smoothing in complex images. Then your risk is a lot more reduced than if you're looking at, say, a 32 by 32 pixel where you could be causing all kinds of catastrophes without realizing it. And then on the second point, yeah, secured data, retrieving your data from safe sources is definitely a thing that academia, I've noticed from my experience, seems to be very switched on about. Like, in my honors, it was a very big question of making sure that, so when I was generating my data set for the textiles, looking at all the different biases, for example. So, because I was going off recycled clothes, they were mostly from Vinnie's, and it's like, what biases does that give you? Because the slightest things can make all kinds of horrific effects. As for businesses, it's definitely something I'm curious about as to if, say, for example, a sleep-deprived, coffee-driven dev is given like 24 hours, 48 hours to build something, are they going to do the rigor they should be? I'm not too sure. Are they even going to build a model correctly? Maybe they'll just try one of the unsupervised ones because it'll take them 10 minutes and they can actually get some sleep.
Cool. Anyone else? Just here, B.
Oh, cheers. So one of the things you mentioned with good security there is trying to not let people access the raw models. One of the main uses for them is particularly if we look at the case of an image sensor on edge devices, which are on devices that ship out to multiple people with the model on it. Is there anything that can be done today to protect that, or is that just free game?
Going back to the model salting idea, part of the advantage to this, purely on a theoretical level, haven't done the tests yet, is that then, say, for example, a company like Cylance, who is dropping these models on disk to each of these different clients, at the very least, you can change that model in some way that ideally gives the same results to non-adversarial samples, but to adversarial samples will give completely different results. So that at the very least, if you can brute force a way to get malware to run on one specific device, it's not going to run on every device on their network or every device worldwide.
That's it. One more round of applause for Edward. Thanks, dude.